Okay, so we can start today's lecture. So today we'll be talking about VLM and as well as image generation. If we recall last time, we talked about the transformer for images, which with a continuous token. Then we also talked about clip, which is embedding of image using contrastive learning. So both are image representations. VLM goes further on that. If you recall the clip, which does image classification, basically it's open vocabulary classification, doesn't strict to specific classes. So that's the advantage. But if you want further doing more things with the images, then you need integrate the image with LLM. So this become a visual language model, VLM. So this is for image understanding. Then we will talk a little bit about image generation. This one is just following the idea about using transformer to generate images. So basically, and then we will talk about a more continuous version of image generation in the later. But this one, we were thinking about generate discrete tokens, then you decode the image. Okay, so that's that's for today. There are two topics. Again, we will talk mostly about the two papers, but we will talk also about the third paper, which is related. Yeah, so basically, the first paper, Lava, is an open source solution to this visual language model training. It's a Actually, there are many other open source solutions if you look at. Currently, the closed source has, it definitely borrowed from that, but there are some slight difference. But open source, if you look at, there are quite a number like Blip and so on. But this one is actually the most popular. Also, it's the simplest. So simple makes it popular. And when you look at that, we will see the architecture and the idea is actually pretty straightforward generalization of instruction tuning for the LLM. So this is the beauty of this method. So this is actually one which is most noticed. And we will use that to illustrate the VLM, basically. How do you train a VLM from a LLM? To get image understanding ability. Yeah, so you can use the same to other modalities like audio, like one way, right? You can or other music or whatever. So this is a general recipe, so-called multimodal understanding, right? Then we'll talk a little bit about the generation using discrete tokens. Because we know how to generate discrete tokens using LLM, then we have to say, okay, if I generate the discrete tokens, how do I actually decode that to images, right? So this is answered by this VQVAE. There are, again, other similar methods. Essentially, the idea is you tokenize image to discrete tokens. And then you use that for generation. So if you tokenize the image to discrete tokens, definitely you can generate, right? So because we use LLM to generate this, we know sequence model. And then, but of course, if you recall the vision transformer, right, VIT, they actually tokenize the image, but using continuous tokens in the embedding space, not directly to the discrete tokens. So if you want to do the discrete generation, think about the standard transformer without modification, you really need discrete tokens. So this is what it resolves, like VQAVE, but there are other solutions. And DAL-E, of course, is OpenAI's model, which I think people probably know that if you play with ChatGPT and so on. Nowadays, they are using more diffusion-based methods. But at the earlier days, even a few years, maybe 2 years back, they are using this. Basically, they are using this discrete token generation. So very similar to what we talk about. Basically, the DALL-E is DALL-E, or yeah, actually I don't know is what this yeah, is what we describe. Basically, the last two, one is how do you describe the image, and then how do you generate, right? So it's a texture generation. So this is just again, we add this like discrete generation just for the completeness. Just aware of there is such a methods. There are actually variations of this theme as well. The more modern is more working with the continuous, more diffusion model or variations of diffusion models. So so they could combine with some ideas here. So there are a lot of possibility to combine different ideas. But basically, yeah, this is a topic. Okay, so the motivation, of course, I think I already talked about that. So we just again just redo this. If we think about the vision language model, right? Visual language model, VLMs, we actually can start in the Lava approach. The simple approach is starting with instruction tuning. Instruction tuning we talked about in a lecture. Basically, it adapts a pre-trained LLM to follow instruction following, right? So this gains instruction following ability. And it's basically the, if you just if you remember that class, what we talked about mostly about is data curation. So essentially, it just continues train this LLM. I think in the homework we also did that, right? The only thing is usually you mask the prompts. Other than that, it's just common training. Okay, so this is instruction tuning. The other thing, if you recall, which because we are talking about the VQVAE, we talk about VAE, right? VAE, if you think about that in the latent representation, which starting point of your decoding into an image, is a continuous, again, continuous model, right? So it's a Gaussian. So VAE try to put everything in the latent space look like a Gaussian, right? So this is something we talked about. And then you decode a Gaussian into image. So this is two ideas. What we want to do here is first doing the understanding, right? So then you want to combine this image with LLM. In particular, in the Lava approach, it's instruction tuning, okay? And for the generation, if I can learn something in the latent space instead of a Gaussian to be a discrete tokens, discrete code, then this code can be turned into an image. Then I can generate a code, discrete code. Why discrete code? Because transformer can generate a discrete code, okay, without modification, transformer, right? So yeah, so basically this is what we are going from technical direction, right? So one is a Lava, which connects a visual encoder to a pre-trained LLM, then do instruction tuning. This becomes a VLM, okay? VLM, of course, a lot of applications, even in robotics, in other things, image understanding. This is really powerful. It has a much stronger image understanding than some other earlier models. For Lava, they start with a clip. You could connect with other image encoders, but the clip is something which pretty useful in terms of communicating with LLM, because clip is a text image alignment, okay? So VQVAE described the data, and then we'll show how that's done. This one we will go probably a little bit quicker. We do show the formulas, but we will not go to too much detail about that, because there are some things. But at least you are aware of how this can be built, discrete token, if you want that. And this one just using VQVAE to do the image generation. So the other one is just using it's just application of VQVAE actually, they use a slightly different discretizer. They are not using VQ, but something quite similar. So we are not going to talk about their decoder, just talking about the VQ, but their discretization is similar, but not exactly VQ. Okay. So visual language model, what you can do, right? It's basically for the general image understanding beyond the classification, right? You can do quite a bit of things. If you recall the computer vision, they talk about the image classification. They talk about, then later on, they talk about the segmentation. They talk about they also talk about detection, right? So there are various tasks. And later on, they were also mentioning about the question answering with the image, VQA, so-called visual question answering. And there are some things, spatial understanding, whatever. So other things become more and more high level. But VLM is certainly one of the popular techniques now trying to dealing with more complex tasks. Liquid image classification. This is a typical image you see in a lot of papers, also in the LAVA paper. This one is just, you can say what you can do, right, with VLM to this. For example, you could do captioning, which basically say, describe this image, right? They will tell you this image, what it, taxi is a city scene, right? And there's a man and so on. So this is an image caption. You can use VLM to do that. Question answering, right? You can ask what is a man doing, right? So it's yeah. So basically doing ironing, right? So and so on. So then you can talk about say how many people, even or how many people or how many cars there, right? So I mean, these are more like a question answering, other question answering, different styles. You can do counting. Then you can do reasoning, basically what is unusual. This is a very popular prompt for this image, what is unusual, right? So that we will later see the Lava's reply. We will give that. Basically, yeah, basically, these kind of things you can do beyond the classification, more to do with reasoning, more to do with the conversation. You can doing a dialogue with this image and so on. So this is what VLM can do. The general goal is you add image first. Usually image is encoded as tokens. It could be discrete token in some approaches, but mostly most approach like Lava or whatever or others using continuous token. Continuous token, of course, if you think about this VIT structure, which we talked about in previous lecture. So we do have a way of generating continuous token. Yeah, oh, I think I didn't. Yeah, so we do have a way to generate continuous token by using blocks of images, image patches, right? So basically, yeah, this is a way of how it's done, and input tokens and plus text tokens, and then you just ask questions, then output the language responses, right? Grounded in the image, which means your response should reflect what is in the image. Answer questions to do with this image. Okay. Now let's think about what you need to do with image understanding with LLM. If I have LLM, I want to give them image understanding capability. What we do, right? Pre-trained LLM. You could also start with instruction to the LLM. That's maybe more typical. But usually you expect the sequence of embeddings or tokens. In the text itself is a discrete token. But the LLM can take an embedded token. If you think about that, right? Just if I say I'll remove in the prompt doesn't need to you generate. It has, when you generate discrete tokens in the LLM. But when you try to use that for understanding, if you think about that in the prompt, the first it turns a discrete token into a continuous embedding. So basically, you can start with this continuous embedding without, which, so essentially, it can take embeddings. Okay, so this is a key. where they are utilizing in this VLM. So you can take embeddings or tokens. But an image is not naturally a text sequence, but it can generate embeddings, right? So this is what pixels are dense, right? So semantics are spatial, and one image may contain whatever other things. How could we integrate image to understanding, right? So this is basically the key parts, which says that you convert image features into image tokens, continuous tokens, and combine with the text prompt. Continuous tokens map into the prompt as continuous embeddings. You discard these discrete tokens, and then once you can do that, then you can just using LLM to continue to talk about that. This requires image text alignment. You think about it. So a clip become natural, right? Clip can naturally convert image into semantically text-like features. So convert image into image tokens, and then so that's a simple idea. So this is basically the key, and there could be other designs. This is the simplest design you can think of because you're utilizing VIT, which turns a block into tokens. You map those tokens into transformers embedding, and then you do that. Okay, so this is a design. Yeah, this is basically, once you do that, once after you trained, right, this becomes a visual language model, VLM. Inputs is image tokens plus text tokens. Image tokens will be continuous in the embedding space, okay? Output is just, just generation. These are generation, right? So that's about it. If you think about the prompts, right? If you give some prompts, instead of giving the discrete tokens, you always give the embeddings because it doesn't require generation. So that's what it says. Now let's look at the instruction tuning to create such a VLM. So this is basically a Lava's approach. As I said, there are other recipes, but this is the simplest and the one which we could look at. If you recall instruction tuning started with a pre-trained LLM, right? And fine-tune its prompt response pairs, SFT, we also call that. And this one gets you the instruction following ability, basically prompt, data. That class, we mostly talk about this guy, data, where they come from, right? Today, we'll also talk about where the data for the VLM comes from. So this one, SFT, goes to instruction tune the LLM. So this is the pipeline. The key part is certainly this guy, right? So, and we have this automatic ways of creating this data. If you recall that there, so in the AI feedback paper, or in the self-instruct paper, and so on. So they all can use itself to create some data with some little bit of human curation to find that. If you get an image, what you do, right? Image, like this guy, right? So, and then you have a visual encoder, which can be a VIT structure, which is the most popular. And when you have a VIT structure, right? So you train that with clip, right? So basically, clip can take the VIT, right? VIT gets you, let's say, 16 by 16 patches, for example. So you have a if you have a 16 by 16 patches, it's 256 total number of tokens. So it's a visual token. It's not one token. It's let's say you have a 256 tokens. Then you can put that into your prompts. This is a visual token. Let's say 256 token, which is basically the number of patches. And then instruction to the LLM, right? So instruction to the LLM. Then feed it to that. Then you fine tune. You need the instruction tuning data. This is basically the instruction tuning on image text data, right? So this one we will talk about how they are created. Well, after tuning, then you are done. You are basically instruction tuned VLM. So this way is you don't need pre-training. You just need additional instruction tuning data to make LLM understand the images. So this is basically a pipeline. This is a Llama, okay, Llama pipeline. Llama starts with instruction tuned LLM as a visual tokens, instruction tuned combined system, right? So basically that's a picture. So then we will talk about how that's done, right? So let's quickly talk about the training recipe, then we'll go through the components. So relative to the text-only instruction tuning, you need a vision front end, right? Converts image into tokens. LLM can use. Keep the pre-trained LLM, or actually instruction tune LLM. I mean, you can do either, but mostly actually people start already being instruction tuned LLM. They can follow instructions already. Yeah. Visual encoder plus connector to produce image tokens, and then train on image grounded instruction response pairs. Right. This basically on the same as the picture we showed earlier. Implications will be architecture change is small compared with the actual alternatives. If you look at the alternatives, there are alternatives at that time. This one is come out not the first one, but they are the one actually a little bit not the first, but it's one of the first, but then they are the most popular. Yeah. The simpler and more effective in some way. Yeah. Of course, the key is getting instruction tuning data, same as the text-only instruction tuning. When you have a visual instruction tuning, right, then you need to create this data. So how do you create that? They have a smart way to create that. So we'll talk about that. Yeah, generation, and also you do some training. Okay, so that's about it. So it's actually simple if you think about that. It's not that complicated. This is also the one of the strengths of the paper. It's simple. Always people like simple ideas. Data generation. So a major bottleneck is multimodal instruction data. What you can do, right? You can either, of course, starting with a VLM already, right? Assuming you don't have VLM, what you do, right? So here is what it does. Use language only GPT-4. So you do need something to generate. You can use a human, but of course, like a self-instruct, you can also use the LLM to do that. They use GPT-4, which are available 2023, right? There are certainly later they have a GPT-4o, if you recall, right? So, but they have a multimodal. But before that, you can have GPT-4, which is text only, to create such data. So start with the image with captions object. So they do have these kind of images. We will show examples, but those are already has data sets. One thing I have to mention, this works because you don't need a lot of such data, right? Instruction tuning, you really don't need a lot. It's not like pre-training. Even for text-only instruction tuning, if you say, I can give you a few thousand or even 10,000, that's sufficient. So this one is kind of similar. You don't need huge data. So, but you have a lot of image with captions. There's some Microsoft Cocoa, for example. They have this kind of data. Treat those as symbolic explanation as a text proxy for the image. They are starting feed into the GPT-4, right? Basically say, oh, this is the image described in text, basically. Then you ask GPT-4 to generate instructions and answers, basically. So you say, it's like a self-instruct based on text only, but a text is already done with the image because image have a caption. Caption tells in convert image into text that tells the image what actually is about. Then you can use this text, right? Just create questions, answering pairs. Then you remove this caption, right? So then you can give this to ask the VLM to say, looking at the image only, not captions, whether you can answer these questions. So basically, this is a kind of trick, or this kind of used in quite other domains for image generation. You have auxiliary data in your training, right? You use that to create the data, and then once you create the data, you don't have the captions. You will be able to directly answer the question about the image, directly gain image understanding ability. So basically, yes, this is the approach. They have a conversation, they have a detailed descriptions, there are complex reasonings, and so on. So if you think about this is a little bit like a text-only instruction tuning. Also, the creation is like a self-instruct. It's like using LLM to create instruction tuning data. But then once you apply to that, once these are created, you can use that to train a VLM. So basically, this is a simple approach talked about in the paper, which is pretty representative of some related, quite a bit related works like that. So these are how data created. Once you have a data creation, then you will be able to train, right? So how do we train? First, we will look at first we look at some examples, right? This is one of these examples, right? So basic captions, I mean, these guys, right? And these boxes and so on. Then you translate into instruction data. Basically, what types of vehicle is right? What are the peoples in the image doing, and so on, detailed expression and so on. So basically, this is just giving some sense of what their image looks like. Yeah, right. But basically, GPT doesn't need to see the image; they just see the text distribution as well as where these objects are, boxes, right? So and then they will, starting from that, they will starting to generate instruction. So you can use text only. These, of course, are curated by human. This is this before the this exists. This text exists in the computer vision data set. So they just take advantage of data and then that's starting to get it suitable for LLM. So architecture. So let's look at the architecture. Architecture-wise, it's a pretty, again, it's simple. So this is a visual encoder, right? You can think about the transformer. You generate image patches, right? Each image patch will be one token, right? Then you project to the same dimension. This is a linear projection. You project this guy. If you use clip, if you think about the clip structure, each text token should already align with text in some way, because clip is image text alignments, right? So each patch you get a projection, and this becomes image tokens here, right? So this, and then you have these language instructions followed. After that, you just say image token followed by language instruction. Then you just fine tune. You get a response, right? You just fine tune. So that's all, right? So this one, the only thing here is instead of using the general embedding layer, right? You use your training as in the LLM, discrete to continuous embedding. You just using projection. So that's all, yeah. So that's all it is. Yeah, basically, once you have that, you are say basically a clip, right? So this is what is used. LLM is a Vicuna is a instruction tune. It's an earlier one. It's not the best one for now, but at that time it was pretty popular. It's a fine-tuned. It's an instruction tuned using GPT generated data on llama, right? So llama. So this is an instruction tuned llama. Connector is a trainable matrix, right? Just this guy, right? So basically, they connect all these patches to image tokens. So image features are projected into LLM embedding space as visual tokens, and then once you have the visual tokens, you are doing the language instruction, then you are essentially get to what you want. So that's basically that's basically it, right? So we just quickly talk about the connector. Connector itself is just each image create these tokens. These are just thinking about the embeddings of image patches in your transformer layer. Recall that the VIT has image batches. Each image batches forms a image token, right? Image token will be the transformer layer comes out of that. So top of the transformer layer get you these embeddings. Then once you have these embeddings, right? So you are mapping this guy. For example, the dimension of the VIT's embedding may not be the same as your LLM's embeddings. Even dimension may not match, right? So you have to do a transformation. Semantics may not exactly match as well. So you do this one basically do a translation, just translate your image, this kind of token into what LLM can understand. This is embedding, and this one becomes an embedding layer of your LLM. So basically, yeah. So that's all it is, and then that's basically you choose image patches, semantics, right? Maps into language compatible embedding. So there are people study. So what these embeddings look like in the language term. So they find something. This meaningful, basically. I mean, it's like a text. If you can decode text, right? So even because it's embedding already in text, you say, oh, what it looks like in the discrete tokens. Then you could try to do that. So essentially, they have some meaningful, but it's a combination. It's more about the combination of different things. So it's yeah, it's basically meaningful. Yeah. Visual tokens and continue with next token prediction. So yeah, so this is that clear? So any questions so far? I hope the architecture is not. This again is the simplest, and this is as far as I can tell, linear projection from VIT top layer to this is pretty simple, right? To the text prompts. Now let's talk about the training, right? So they have a staged training, but this one is doesn't matter much. We will go a little bit quick on this. They first want to align the features. They think before you're training everything, right? Your W matrix has to map your visual tokens, the VIT to your visual tokens, right? So correctly, right? So basically using tetra pairs, freeze the visual encoder, freeze the LLM. So basically you say, okay, I just want to, this one, they're okay. I just want to train this W connector, right? Train omnilet projection W so that your visual is really looks more like the text token. So learn a visual tokenizer that maps image features into the embedding space expected by the frozen LLM. So basically, this is the first stage. It just makes training easier, and so that W is already kind of, you can call that pre-train of W, right? Kind of meaningful. And then after that, you can fine tune all of that, right? So after that, so this stage 2 is a visual instruction tuning. You basically you basically training format, right? This basically image plus instruction to the answer. I mean, this is a typical ways of that, right? So I mean, it could be user equals something, but I think the paper has a slightly different encoding than the more modern ones. But nevertheless, this guy's an image token, instruction. You need to answer, right? So, and you are optimizing the next token prediction. This one usually you mask out this guy, right? So this one you don't need the text token prediction, especially. You just predict the answer, right? So basically, yeah. These are typically masked out, yeah. Same as in the text case. So yeah, that's all. So basically, then you just fine tuning the whole thing. Once you have this guy, you can backprop everything, right? Backprop back, even backprop to your W, and then you are training. So yeah, so basically, I mean, this is LM weights and the visual encoder depends. You could choose this to be frozen. You can choose that to be trained, but the frozen is pretty reasonable here, right? But generally, you can train LLM because LLM still need, because there are some misalignment of image tokens with the typical text tokens, right? They are usually mixed of a lot of different things, so you still need to try to modify the weights to get better and width. So that's all. Yeah. So basically, pretty simple, the pipeline. If you think about the simple architecture, simple data curation, similar to self-instruct, and then you have a simple fine-tuning process, very similar to SFT on your instruction tuning data. So from text instruction tuning to what is training format? Training the format, if you have data, you could just you could basically do the LLMs. Yeah. So essentially, it's basically to fine tune your study. So basically, the stage one is using the using the caption, right? So basically, yeah, basically caption, you can decode the caption, which are supervised, and then basically you are training this, yeah. So yeah. This one, I think if you do very complex things, I'm not sure entirely how much this buys you, because hopefully you could train all of them together. But because LLM usually have a lot of weights, so essentially you really the first if you just fix this weight, it might work in the one. Yeah. So basically, it's more staged in the sense of you first focus on this guy, right, rather than LLM. But certainly data is slightly different, but probably this guy is more important. Yeah. But anyway, so it's nevertheless, it just it's not a complicated structure. So this is lava, and it's very efficient in the sense we don't need a lot of data, right? So this is the same, again, this is the same as a text instruction tuning. Text instruction tuning, you don't need a lot of data. Visual instruction tuning, you do not need a lot of data, because pre-trained LLM already know a lot of things. Visual side is only need, mostly it's about this W, if you think about, mostly about this W, right? Translate your visual tokens into text tokens. Of course, because text tokens is slight mismatch the original, so your LLM needs to be adjusted. Yeah, but nevertheless, that's what about. We don't know exactly what happens with visual token, but we just train that as information, right, provided to the LLM. It doesn't learn the language from scratch. Same as the pre-training to instruction tuning, it just learn the instruction following. So basically, this is what happens with this instruction tuning. Okay, so here is the result. So what you can get out of this, right? So you have basically you have image tokens, and what is on Europe by this image, and this is a popular prompt for this. Right. So and for that, and then expect a response in the paper. The unusual X value is a man eyeing clothes on the back of a mean man or man. Yeah, it should be taxi, but it's close. Yeah. And GPT, unusual thing about this image is a man is ironing clothes on an iron board attached to the roof of a moving taxi. So this is certainly better, because this is a much smaller model, right? So this, these are some other approaches. Again, I said this is actually more complex, and Blip is also pretty influential, but it's more complex, and essentially it's less used later on. I think Lava is regarded as a better, more modern approach. A man is sitting on the back of a yellow taxi. So this is not as good. Open Flamingo is another one. It's some others. So man it's again a little bit different approach than in this. Yeah. Compared with this, I think this is the simplest approach, and also it's more effective because they are utilizing LLM more. So basically, they give a lot to the LLM. If I have a strong LLM model at that time, it's Lava, right? Lava is already the state of art at that time, so it could doing pretty well. Later on, of course, there are evolutions, but you know the main idea remains very similar. Even there's evolutions, there are other models. There are models which are specifically trained for visual, not just in the instruction tuning. If you see the people release these visual language model, multimodal models, they are enrolled that training into much earlier stage. Right? But again, the idea is very similar. So you can see from this what they can do and roughly what kind of formula you want to use. This one can be varied as well, but this is representative. These are some quality results. Again, because they are comparing with some well-known. There are other things, but this one they choose to compare. There are various actually a few other models at that time, not only this one, but they are doing well. So basically, this is what they are trying to say. Basically, simple approach is effective. So if I have a one sentence conclusion about this. Summary, right? So essentially, if we get a quick summary, so what we have is a visual instruction tuning. It's a multimodal extension of a text-only instruction tuning, right? So you need an encoder. So the only thing you need an encoder. Visual instruction tuning is a multimodal extension, and you can think about you can use any other modality, not only image. As long as you translate those modality into sequence of tokens, then you can use very similar things to start to do that, right? For example, you could, in principle, directly understanding your audio, for example, right? So you just without first doing a translation, right? So you just encode your audios into audio tokens, continuous tokens in the embedding layer, the same thing, right? And then you're eventually you say, for example, translate that or whatever. Then that gets you whatever can be talked about as translations, something. Essentially, you know, this is a very general framework. I say is, I mean, just visual encoding, but you could doing a lot of other things. A pre-trained visual encoder plus pre-trained LLM can work surprisingly well with a very simple projection. This is also shown because, as I mentioned, although when I present that, it looks straightforward, but when you come out with it's not that obvious, this one will be the one work well. There are much more complex designs, as I mentioned. Yeah, so people would first think about complex things, then later realize the simple things work well. So it's not non-trivial, even though simple. Simple doesn't mean trivial. Yeah. Data generation is central, right? So you how do you generate? Turns out that they have these ideas about using GPT-4 and synthesize some instruction following data with the assumption that the understanding ability is more or less already there. You just need to bring it up by using this data. So you don't need a lot of data. You are not just training the inherent ability. You are more training about how they follow instructions to interpret these visual tokens, which is a much easier task. The more primary understanding, response generation in language, not in synthesis. If you recall, you can say multimodal understanding. So this one achieves that. But it doesn't achieve the multimodal generation, right? So generation, you have to do something. So in the current, a lot of models like a Gemini, like a Nano Banana, right? So all those more modern models, they have a more integrated, in the sense that they could do part of multimodal inputs as for understanding. Also, you can generate as a part of models the sequence, right? Essentially, you encode everybody into the sequence, right? And then, but you can part of it can be understanding, part of it can generation. So it's much more blurred. But this one is more. It's a little bit earlier, so it's more about just solely for understanding image. Under generation, right? Generation, we will starting to talk about that in the future lectures as well, more in the continuous generation. But today we will starting talk about this topic in a more simpler form in the discrete generation. generate images. You want an LL style model to generate images. You can either generate a discrete token, or you can generate a continuous token, and then you can embed back, right? If you generate a continuous token, that is like using diffusion model and so on. Those are the things which are nowadays more popular. But we will talk is about today is another approach which can be useful for some other applications, right? Also, it's used for OpenAI for a while. Essentially, they are generating image using transformers, but the image representation needs to look up discrete tokens. Once you do that, you could do generation of these discrete tokens, right? Just formal by using sequence model, just using, yeah. So this is basically, yeah, the next question we will talk about. Of course, we already mentioned that this, what is achieving that, this is through by VQ VAE. So let's look at that. Recall VAE. So VAE and the latent generation, right? VAE start with a probabilistic model, latent variable Z, which comes from a Gaussian distribution, right? So, and then given Z, you generate your whatever your image X. So if you recall that, this is a probability model. First generate a latent variable, then given latent variable, you decode into an image. This is a decoder. This is your decoder. This one is, yeah, this one. This one can be if you're given image X, this one can be done by using encoder. But essentially, this one, the idea is this one is looks like Gaussian. So why latent variables are useful? They compress dimension information. It makes it easier to generate, right? So they give a form we can sample, which means it's a Gaussian, right? So, and then after you do a Gaussian, you can decode, right? So basically, generation becomes simple. It's a simple structure, and in the traditional VA, it's a Gaussian. But here we want to say we want to do that with a discrete code. Can we model this instead of a continuous Gaussian? The decoder is the same. So once you have the code, you can use whatever decoder you write, right? But a continuous Gaussian is harder to do with transformer. So we want to say let's do a discrete code, right? So this is yeah, discrete tokens, continuous latent, often Gaussian. VQ VAE is a discrete latent code. Of course, the purpose is generating using transformers once you can do that, right? So this is yeah, this is the only thing. So how do you do that? The question is, right? Because discrete has some issues, so they have some tricks to train such a discrete code, which we'll mostly talk about. Again, we will talk a little bit probably more at a high level. The details, I don't think that will be the exam, that the details of the training, although we will go through that, but the details, not training, right? So discrete representation of a sequence generation, right? Continuous natural for VAE, but they are not ideal for token style, transformer, sequence modeling. If we think about design property, what it is it has to be convert the image into a sequence of discrete symbols, right? And then you can learn a prior over these symbols. This prior basically say just a sequence model. Yeah, you can do that sequence, right? You think about image patches. Image patches, if you have a 16 by 16 image patches, it's a 256 tokens, right? You need to generate these 256 tokens. Each patch you can either encode from image or decode back to the image. So this is something. So you always think about image patches. Yeah. Sample these symbols autoregressively, then decode back to the pixels. And this is basically the pipeline you want to think about, right? So of course, transformer, we know how to do that. We will quickly later talk about this, this DEL thing. But then before that, the key is how do you create some VAE discrete-like? So this is VQ VAE image to decode code and decode to contraction. So this is basically how they train this, just like training a VAE, right? So, but this one you train a discrete token sequence. Yeah. So these are their architecture. So the architecture looks like this. So maybe I'll explain that. This is, this one is a little bit early. So they are not the transformers, or they are not thinking about transformers, but you know everything can be applied with transformers, right? So we just say this CNN, then we do CNN. This is encoding, right? CNN, after encoding, you get a latent space. Latent space is some dimensional space, or whatever dimension is, for example, 512 dimension. Then in this file dimension, you want to discretize that. So this is discretization, codebook, embedding space. K, I remember in the DAO is something like maybe 8,000 or something. We can check. We have this number, but something like like this token, right? So it's thousands or tens of thousands around that range. So let's say you have 1,000 K, right? So each one is a discrete token. This is representative about your image. Basically, if you think about even given the embedding, what will be the best token representation? You can use the k-means algorithm, right? K-means algorithm is a clustering algorithm which will minimize the difference in that. So you can think about this one is trained with a k-means on this latent space. Once you have the continuous encoder, after k-mean, you get a discretization. Yeah, it just have a lot of k. It's not a small number of clusters. It's many clusters. But essentially, you could get this code book with good approximation. And then this is a quantization. Basically, this one just say, oh, I have an image patch, right? And each one is given one of the code book's value becomes discrete, because this one I use a k-means approximation, but then each vector associated with a cluster number, right? That number is here, and then basically you just encode the image into a discrete now, right? So then after that, once you have this, right, you have a discrete encoding. You are associated with each discrete encoding associated with this VQ vector, right? You take this VQ vector, you fill in your image, becomes discretized image patches right here, and then you map back to your image. So this is a decoder. Yeah, this is a decoder. Encoder gets to continuous, decoder from a continuous vector, which is one of these VQ, to your image. So those doesn't need to change. The only thing changes is from encoder to decoder, both are continuous. There's a discretization. Discretization is through k-means, basically. Yeah. So basically, this is if you look at this, this one, they will talk a little bit about when you say gradient. Essentially, what it does is the following, right? So encoder here, when you do a k-means, you're changing that to be a slightly different vector, right? So this may not be one of these k1, ek. But this one is the closest to your encoded image. So basically, you're mapping this one to that with a small difference. Yeah, usually it's small. Yeah, the difference, for example, this one is E, right? This one is actually your code. I think this is encoder right here. This one is where the E comes in, right? So the E comes in. If you think about training that jointly, right? So what do you want to take derivative? Going back to the encoder, right? Decoder, of course, you can take a derivative. That's easy. All the parameters is just a backprop, right? So your forward come here, backprop here. But here there's a discontinuity. The idea they said is so-called, I think through. Basically, you say, oh, here is a derivative to this. This is where it carries over. And then this guy carries over to your actually here is where you shows up in the decoder, right? E is the code book shows up in decoder. There's a derivative here. Derivative here, then you copy that to this guy. Basically, copy this derivative to this, and then you continue doing that chain rule. Yeah. So basically, there's a copying. This is basically just a trick. Yeah. So how do you train that? Because you want to pass your backprop both from the decoder and the encoder. When you get this discontinuous case, you just copy. Yeah. Okay. Later we'll have one slide to say that. Basically, that's it. Encoder out a continuous representation, which can the ZE, right? Quantization maps it to the code book, which basically you have a k-means objective to make a small residual, and the decoder reconstruct image from the quantized. Quantized is E1, E2, whatever it's code book. Okay, so this is how it's done. Yeah, if you look at that, it's still, I mean, simple. I mean, in the sense, right? This is encoder, this is decoder, and the only thing is have a discretization. Then you have a trick to say, okay, what's wrong with the discretization, right? If I say k-means, nothing's wrong here. If I say, if I will say, how do I make a propagate back, then that's a challenge, right? There's a discrete, then they have this idea, basically. If you have this idea coming from another paper, yeah, this idea, then essentially they can backprop. So then you can train that. The whole thing that you train, okay? Discrete quantization with this guy. Encoder output continues, but quantized by this guy. This one is essentially nearest neighbor, right? Nearest neighbor lookup, and this objective is like a k-means if you square that. Okay. So yeah, so basically this is what it is. Yeah, so basically, you know, you just force that map to a set of discrete code or tokens. VAE, yeah, it's a Gaussian, and this one is a discrete, right? So that's about it. That's about the high level understanding of this. Basically, you can use a similar VAE structure to make it discrete. Here is a loss function if you write that, but you can separate. You can think about first, this is reconstruction. Of course, this is the decoder, right? So from your VQ to decoder, right? This one says this is decoder training. This one says codebook update, right? Codebook update is basically says this is using k-means objective. This one stop gradient. So you are fixing your encoded image. I normally update my z, and then this one is smallest. Okay, so but they add them together. So for the reason, whatever reason, but essentially it's kind of like a k-means objective. So this is nearest, if you recall, right? So and this one is something more about so-called commitment loss in the paper. It's more about fixing my Q. K-mean, you have two updates. If you think about given assignments, right? You are minimizing this code, and this one just say try to make once I have the code book, my encoder training should be close to this. So something like that. Yeah, this is more to do with this. Encoder training, yeah. So this is what it actually does. Input. This one is the encoder, and this learned code book. This is part of the parameter, the model parameter. So you need to learn all those. So these can be considered learnable parameters. Okay, and this code book close to that, and so on. So yeah, reconstruction trains the decoder. This guy's code book loss, right? This moves the select code book towards the encoder because this one stop gradient. This one move this guy to this guy, right? Encoder outputs. Commitment loss prevents the input output. Essentially, you can say train encoder, but in reality, encoder you can also go from here by through by this through, yeah. when you have VAE, if you remember, you have encoder, decoder, right? So they're all coming from here, yeah. But basically, that's all, yeah. So stop gradient operator means, yeah, basically in this PyTorch terminology, you just stop gradient. You don't train the parameters. When you take gradient, only take this guy, not with respect to this guy. Yeah. So that's yeah, that's about it. We will quickly talk about back through this one we mentioned in the earlier. We just quickly talk about that. So the nearest neighbor assignment is not differentiable, right? So using a copying operation, if you look at in the picture, they also show that. So forward pass go through the quantized code, and the backward pass copy that, and then you can continue doing that, like in your autoencoder type of setting training, right? You can copy that. You can go through this one to the encoder. So yeah, decoder tells encoder how to move so that next forward pass may select the better both book entry. So that's about it. This is one of the central technique idea of this paper. Basically, this one is coming from others, but they realize that this one can be jointly trained in the encoder. Yeah. So now let's yeah, this we do some high level just understanding. There's a way to do that. You just put in a bunch of different loss functions, and then you do this trick, the copying for the backpropagation. Then eventually it's possible to successfully train a discretization of image. Make an image a discrete token. Basically, this is what it is. Give a discrete vocabulary, right? Once we have the discrete code, we can use a transformer to do that. Each one is an image patch. Each one you can think about it is an image patch, and then you just code one image patch at a time. Then you have transformer prior to do that, and then you have or a text condition prior. Yeah. So basically, you could also do the text condition, right? Basically, this is what it is. Yeah. So full generation pipeline, you first learn a VQAVE tokenizer and decoder, right? So this one just using the VQAVE, then you turn an image into discrete token. Your ability to turn the discrete token into image. Then you train transformer on the discrete token, optional condition on the text tokens on the same sample codes, and the decoder to the pixel. At this point, I can mention, right? So if you think about it, you have the ability to turn an image into discrete tokens. In principle, you could also use this discrete token directly just, in your LLM, right? Without, if you think about that, then you just these are discrete tokens. Then you can add that to your vocabulary, vocabulary, so that you can also achieve a kind of visual language model in some sense, right? People don't do that usually because it's much more convenient for the image to do the continuous token. But this illustrates if you really want to discrete token, there's a possibility to do that. Okay, so yeah. So basically, yeah, this one is a mapping image into the discrete token and the mapping back. So okay, so now once I have that, this is the pipeline. So this one, of course, this is the example for that. Same two-stage recipe, right? So training setup. Stage one using a slightly different VA. But it's also discrete, basically. It have 256 by 2 into 32 by 32 discrete tokens. Basically, these are image patches. And the image token take one of these, yeah, these are about 10,000, yes, yeah, it's 8,000 values, right? So basically, this is how this vocabulary looks like and how it works. Stage two, then you have a transformer, you have an image text plus image token, you do that auto-regressively, and then that's all, yeah. So then you are done, mostly, yeah. Captions use up to these tokens. and the training with internet image text pairs. Basically, once you do that, you can use this, right? So basically, you're just using this text and so on to generate. So this makes things easy. Once you have the discrete tokenizer, you can do both understanding and generation, if you think about that, right? So do both understanding and generation simultaneously, because transformer can generate. They can also understand if you're just thinking about lava with a discrete token. It's doable, right? So you can train that, okay? But this is focused on generation. Yeah, these are closely related to that. Just a different training formula. We will not talk too much about that, but basically achieve the same purpose. Right, at generation time, you have a prompt, right? And the prompt is here, right? You have a generating image tokens. This one can be generated using transformer, right? So it's just LLM. And then your decoder. Decoder is plugged in using your DVA decoder. And then, yeah, it goes to pixels. So that's all, yeah. So basically, this is basically the pipeline about doing that. So here is one example. They can generate. Yeah, so this one from original paper. I think later on they make it better and so on. This one is a little bit lower resolution. I believe it's yeah. So and later on, of course, nowadays people generate a much higher resolution images. Used to be 5 to 256, then 512, and 1024, and so on. They just prompt is an illustration of this guy in the Christmas. They actually the main thing is they can show they have something which cover that. Yeah, the semantic autoregression. You have a text, right? Then this generated image tokens, 1024 tokens, and then each one is one of these roughly 8,000. Vocabulary, right? So, and then you decode to the image. So this is an example of that. Of course, the reality is nowadays people use diffusion models, right? Just want to still mentioning, but this one is a kind of an interesting approach. You realize that there are many different possibilities, especially if you want to say, I want to make image discrete token. It's possible, yeah. Just illustrate here. Okay. Let's talk quickly talk a little bit about lava versus VQVAE, right? If you think about multimodal AI or LLM, let's talk about the LLM-based AI, right? So then you need to say all the modality needs to be tokenized. So that's a key, right? Both illustrate the ways how do you tokenize that. In either continuous token or discrete token, so that they can work with the LLM. So if you receive the message here, then that's basically the key message in this lecture. So you could tokenize a lot of modalities. Think about tokenization combined with LLM, right? Representation, how do you encode the images? You can have a different type of tokenization. So all this currently we say is image patches tokenized. Now how do you talk that? You basically you have this connector, right, in the lava case, right? In the other case, they add to your vocabulary. In other case, discrete image token add to vocabulary. Continuous token, you just need a connector to map. Training signal, right? Training signal is instruction tuning for understanding. You could do other things, by the way. So right now you could do more than instruction tuning, but this one focus on the instruction tuning is sufficient to bring up the ability for LLM to actually already to understand the image. Then for generation, you essentially using sequence model for the discrete token. You could also to generate a continuous token. If you think about that, you say, oh, I generate discrete token. You say, can you generate a continuous token? Yeah, LLM. The answer is yes, you could. So that's where when you combine it with diffusion model, you could do that. But for now, without any modification of a transformer, you could do that with a discrete token. So this is something. Of course, we talk about this representative work. It's a continuous token. It's a lava. Directly talk to the, for the understanding, direct talk to the embedding layer. Yeah, so VQVAE is a discrete visual codes modeled by the autoregressive prior. So basically, this is a continuous token, discrete token, understanding generation. So that's two. And if you think about this idea, it comes up with a lot of other things. And it's actually recurring patterns in a lot of multimodal. You can do a lot of things. You can essentially, you can encode anything into LLM. And after LLM, you could also generate anything. Once you have understanding this tool, right, you can quickly think about, you don't have to use a diffusion model. Diffusion model give you additional possibilities, but just using these two ideas, discretization, continuous, right? You can do understanding any modality. Say graph, you could do that, right? You can use that to do generating materials or whatever, right? Those are not necessarily synchronized. They have some other structures that you can do that. And you can both do the understanding and the generation. So this is a very powerful idea, basically. The idea, and certainly the currently moving the, I think the fields in the multimodal sense moving to the omnimodals, right? Those have similar ideas, basically. At the fundamental level, similar. Of course, there are something other techniques introduced, but at a high level, they basically pretty much very similar at high level. Summary, so Lava extends the logic of instruction tuning from LLMs, text only, to image understanding. And there's a key notion about the image tokens, which make this possible, putting into embedding layer of LLM. So this makes it possible. And main ideas, the other thing I want to say that if you think about the lava, right? So let's think about, if you think about some other more complex design, right? You could say, oh, I can do a cross attention to my image, right? So this is one example you could do. That you think maybe bring up more information, right? Cross attention to your image. What it does is that instead of doing that, I translate things into the same space in the text. And of course, in the autoregressive model, the text already cross attention to your prompts, right? So basically, that's a simpler design. Yeah, you don't need to very complex to say how do you leverage my image. I just say how do you encode my image to LLM space so that LLM can handle. Yeah, so this is one of the subtlety. It's a main idea. GPT assists the data generation. This is where the self-instruction is being extended, and the simple connector and the two-stage training, and then VQVAE. The idea is basically, you want to have discrete tokenization of your image. Right? This one by VAE, and then with discrete tokenization. Okay, so this is basically what it does. You can do other things, discretization with other. This one just give you the idea. If you think about anything, right, you could actually try to discretize that and then leverage even that clip space or other space. You could do the similar thing. Discrete image token autoregressive possible, which connects actually to text to image. So basically, this is how it works. Yeah, so I think that's about it for today. So basically, how do you make image and language work together, or at least the sequence model work together. After this, we are pretty much done with this multimodal. We have just a few lectures there. You can really do a bunch of other lectures. We will focus, shift to the continuous generation in the continuous domain. Okay, right now, if you think about generation, it's a discrete, and then they convert it into continuous, right? We will next, I think in the other lectures, we're all talking about continuous domain directly. Okay. Okay, thanks. So that's all for today. Yeah.